So in this part of the waveguide, we have not still reached waveguide. We are discussing about wave. So before going into 2D, let me conclude this part. Remember that all the 1D wave equation, they satisfy this wave equation. So it satisfies del square y. So remember, y is the displacement, and whatever is there in the denominator, this is the direction in which the wave is moving. So x is the direction in which the wave is moving. So it's given by 1 by c square, okay, del square y. So this is the double derivative, time derivative of the displacement. So this is what this equation, this is a wave equation that the 1D wave follow. Remember, this x is always the x in which the wave propagates. Agreed? And this c is the velocity with which the wave propagates. So now we'll move to 2D. So in 2D, so consider we will now discuss 2D wave equations. Okay. So let me start with the wave equation that the 2D satisfies. So consider you have a rubber membrane. Yeah, consider you have a rubber membrane. So this rubber membrane can fluctuate. I mean, you can make the membrane like this. Agreed? So you can make the membrane go like this. So when you make the membrane like this, you see, so consider this axis is your x-axis, and say this axis is your y-axis in which the membrane is lying. So the membrane is lying is the xy plane. Now consider this axis is the z-axis. You see, all the vibrations, they occur in which direction? They occur in z direction. So what is the wave equation? Let us start with writing the wave equation. As we have said that the vibration is happening in z direction. So z is a function of x and y. Why z is a function of x and y? You see, initially y here in 1D, y was only a function of x, because y was giving you the displacement at particular x. So when you reach a particular x, what will be the displacement y? That was given by the 1D wave equation. But in 2D, you see, the entire object is a 2D object, and each point on the object has two coordinates, the x coordinate and the y coordinate, and the vibration at each point. Now since this point itself has coordinate x and y, so the vibration of this coordinate and in at x and y will be given by z, because in z direction the vibration is happening. Now, so let me write the equation. Yes, let me write the equation. So now where is the propagation? The propagation of the wave can occur not only in x direction but also in y direction. So this is the wave which is propagating in the x direction. But consider you make some disturbance in the edge of the notebook. So when you make some disturbance in the edge of this paper, so consider this is a paper and you made some disturbance here. So how is the disturbance going to travel? Your disturbance usually they travel like this. It has a tendency to travel in this manner. So this is difficult to draw, so maybe it looks like this, and yeah, something has happened to the paper, and this vibration, they go in this direction. So you see, so not only in the x direction, but the vibration can go in the y direction, and the vibration can go also in the direction in between x and y, in between x and y. So the wave equation, as I said, the denominator of the wave equation always contain, so you see the denominator of the wave equation, look at the 1D case in the left hand side, the denominator of the wave equation always contains the direction in which the wave is propagating. So in this case, the wave can propagate in both directions. So I will have what? D square z by d x square, and I can have d square z by dy square, since it is since it can propagate in both the direction. And this side it will be same, 1 by the velocity of the wave with respect to double derivative of z with respect to time. Now please understand that z is a vibration. I mean, z is the displacement of the particle on the paper, on the 2D paper, and each point on the 2D paper is a function of x and y. So z will give you the displacement of any point on x and y at any time t. So z is a function of x, y and t. Now question is, what is the solution? So how can I write the solution? So this is tricky. Now, so z will be a. So remember, I can write equation in the form of e to the power. Instead of sign, I can also write e to the power. So for example, in 1D case, the equation will look like what? E to the power I. Okay, I can have omega t minus kx. So this is another form of writing the wave equation. So you know all this stuff. These are all +2 stuff. So I am now trying to guess what will be my 2D solution. So I can write a e to the power I, everything is okay, but here I'll have k dot r. Okay, I'll have k dot r minus omega t, and this k dot r can be written as, so k will have two component, kx and x, this x comes from r, and the other component of k is your y, and the big Y here comes from the r. So this is the wave equation in 2D. Now how to make this more intuitive? So I need to define what r is, and I need to define what k is. Agreed? So what was k in 1D? K was the direction in which the wave was propagating. Agreed? This was k. What else k was? K also carried the information of wavelength, because k can be written as 2 pi by lambda. But we are least concerned with this part. So the more important thing is k is the direction in which the wave is moving. Agreed? Now what is x? X is any point at which you are calculating the displacement y. X is any point at which you are calculating the displacement y. So remember these points. Using these points, I'll try to make this part more intuitive. So let us see. So consider this direction. Agreed? Now this is a wave. You see the dotted line and the full line, the dotted line and the full line. So this is a wave propagating in this direction. So how to imagine this? Remember when I said if you put some disturbance in this paper here, then this disturbance will travel in this direction. Agreed? And how the disturbance will travel? This disturbance will travel in the form of crest and trough in this direction, and that will be a 2D. So in this paper here, in this paper, if you produce a disturbance here, like you blow some air, then that disturbance will go as a 2D wave in this particular direction. Agreed? So this is drawn here. So you see that the wave is moving towards the k direction. So the k in the first equation here, this k is the direction in which the wave is moving. Now you see the direction in which wave is moving, k, can have two components, k1 and k2. Agreed? So this is quite logical. So k is gone. Now what is r? Now what was x in this part in 1D? What was x in 1D? X was the distance at which you are calculating the disturbance. Okay, x could be anything, and x always originated from the origin, and it can go anywhere on the wave. Similarly here, your r, that is k dot r, this r is from origin to anywhere you like. You want to calculate till here, you can keep your r here, or if you want to extend your r and do the calculation on this crest, you are welcome to do so. Or you, if you want to keep your r small and if you want to do calculation here, so you are welcome to do so. So what is r? R is the distance from origin, from where the wave originated, to any point on the wave where you want to calculate the disturbance. So where you want to calculate the disturbance, because x and y is the point in which you want to calculate the disturbance, and in 2D the x and y is incorporated in r vector itself, because r can be written as xi plus yj. Agreed? So specifying the r means you have specified the point at which you want to calculate what is my vibration in z direction. You see, I have not represented here z direction. So z direction is out of the paper or out of the screen, in which the vibration of the wave is actually occurring. So let me give you an example of 2D vibration. Consider a tabla. So when you beat on a tabla, or consider a drum, when you beat on a drum, what happens? The membrane of the drum starts vibrating, and the membrane of the drum actually has 2D waves. So I gave you an intuitive understanding of what K is, and I gave you an intuitive understanding of what R is. And I also said why K can have two values, because K is the direction in which the wave is moving, and that direction can be anywhere. And since the wave is moving in xy direction, so K can be broken up into two components along x and y direction. Agreed? As I said, the dotted line represents the trough and the full line represents the crest. So distance between any dotted line and the crest is actually lambda by 2, or you can say the distance between any two full lines, that is any two full crest, is the wave length lambda. So understood what information does a 2D wave carry? The 2D wave carries the information of vibrations. So what vibrations will happen to a 2D object at points x and y? Since the 2D object is made up of, so it's a 2D object is 2D, so we need to specify the entire object, we need two coordinates x and y. That's why we have z as a function of x and y. So what is k? K is the direction in which the wave is moving, and what is r? R is like x. So if from origin to any point on the wave at which you want to calculate your z. Z is the displacement. So as I said, what is z? So if this is your x-axis and this is your y-axis, and if the paper becomes like this, if the paper becomes like this, so if you make the paper look this, okay, then this trough, this crest produced on the paper is also a disturbance, and you can calculate from this point to this point, like so consider the paper has got bend, and you can actually calculate on the paper what is the disturbance. So this disturbance is z, and you can calculate on the entire paper the disturbance. So z is a function of x and y. So we saw what is the wave equation. Remember the wave equation that it satisfies? It satisfies the 2D wave equation, and this is what z is. Agreed? So now what we'll do is we'll discuss what happens when you confine 2D waves in a 2D plane. Agreed? So that will be the basic discussion of our waveguide. So in the next lecture I'll give you a hint of waveguide, and using that we'll go to the waveguide in electrodynamics. Agreed?